All right. I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Thank you for these students. Just pray that you just bless this class. Just help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. So, I just gave you back your mission 1. For the most part, the small and, somewhat important. All right, so I asked that you write on one side to help the grader with his grading as opposed to writing with 2 sides. Some of you written on 2 sides. It's not the end of the world, but, try to adjust and just write on one side going forward. If you've already written mission 2 out 2-sided, then so be it. I will not count it against you since this is coming kind of late to you, this correction. I understand that, you've already written it 2-sided, so fine. If you've done that, it will not count against you. But do otherwise try to, adjust to the demands of the grader as severe as they may be. Okay, so today we're talking about A-differentiability. We are slightly beyond the notes that I've posted, and the reason is simple. I'm not done, and I'm sorry about that, but I will catch up, I think, pretty soon. I think probably, if everything goes as planned, I'm hoping either later tonight or tomorrow at the latest, I should have the notes that cover at least through the end of this week and maybe beyond that. So just an update on that. And then, of course, I should write your third homework, which all of you are like, hey, so many people are asking me, like, where's homework 3? I want homework 3 to work on. Like, why didn't you give it to me yet? All right, fine, no one has said this. It's true. It's actually true. No one has said this. It's still working on homework 2. Oh, yes, there's that. But there is a mission 3. It's in my brain at the moment. Hasn't made it to the LaTeX. So today we're talking about A-differentiability. All right. So here's the, first of all, I should have a little discussion with you about, why we need Cauchy differentiation, for the algebras we consider. So in the standard complex analysis course, typically at this point in the course, you're given the definition of complex differentiability as follows. All right, so here's the definition, usual definition, not going to be our definition, but, well, you know what, this would probably be a definition that I give you to work with for one of the homework problems in mission 3. Because it is the standard fare, and it would be healthy for you guys to think about this way of thinking, because it also gives you a way to, it gives you a chance to revisit Calculus 1, if nothing else, all right? And the definition is just this. If f from the domain, which is a subset of the complex numbers, to the complex numbers has the limit below existing, then this defines f complex differentiable at z. In particular, the limit I'm talking about is this. F prime of z is equal to the limit as h goes to 0 of f of z plus h minus f of z divided by h. So this is the standard definition of the existence of a complex derivative and how you calculate it, right? This is a difference quotient, right? Remember Calculus 1, we say that the derivative is the limit of the difference quotient, like this. If it exists, the function is real differentiable. If it doesn't, it's not. And that's kind of it, right? And you can do this for complex just the same. And why does this make sense? Yeah, because the complex numbers are a field. So this is division by a complex number, right? Which is fine, right? As long as what? Makes sense for what? h not equal to 0. But do we allow h to actually be 0 in the limiting process? We do not, right? That's the whole epsilon delta business. I mean, that's by construction to avoid the actual limit point itself. So this does make sense. And you can prove all of your favorite properties of calculus follow through. Like you've got a product rule, you got a sum rule, you got a quotient rule, chain rule, all that stuff. You can prove all of that stuff in almost the same way that you prove it in calculus 1. Okay, so none of you proved it in calculus 1. But if you had proved it in calculus 1, you'd prove it the same way. All right. So what's the trouble for us here? I have foolishly endeavored to try to teach you guys a little bit of hyper-complex analysis, right? More than complex variables. So what's the trouble with this definition? If I try to use it for even something as simple as a hyperbolic number, like what if I said the hyperbolic derivative was defined as such? What would the trouble be with this definition if I was to try to adapt it to the hyperbolic numbers? Right, zero divisors. So if we were talking about hyperbolic numbers, we'd be in a lot of trouble, right? Because you got these pesky zero divisors at the lines y equals plus or minus x, right? The zero divisors of the hyperbolic numbers, right? And we cannot divide by such numbers. So if you think about the limit, right, the ordinary garden variety limit as h goes to 0 would hit all kinds of zero divisors, right? So how do you work around that? Well, there are two ways to do it, right? The one way is to use the definition I'm about to write down, all right? The other way, which you'll find in the literature, a certain part of the literature on hypercomplex analysis, is to use what's called the deleted difference quotient. So what some people do is they like, fine, I'll just ignore the zero divisors, and I'll take the limit in the complement of the set. I mean, I'm just going to forget about zero divisors and take the limit in the units. So they'll just say h in the units of the algebra. Basically, just add this stipulation to the limit, right? And it actually still makes sense. And you can define differentiation by such deleted difference quotients. That's not my approach, but I study the relation between that approach and the approach I'm about to write down in a section of my notes, which I'd invite you to read. I probably won't cover it in class. It's very technical. But ultimately, what I prove in that section is for the examples people are most interested in, these two viewpoints are equivalent. However, for examples people are less interested in, but I'm interested in, the definition I'm about to give you is much more robust. And is to be preferred because it allows us to study differentiation for functions over a wider class of algebras. Algebras with so-called nilpotent elements, like dual numbers. The deleted difference quotient, this way of thinking is bad. It's not a good way to look at it for things like dual numbers. It doesn't give for example, in the dual numbers, if you study it with the deleted difference quotient, the identity function, if I remember right, even the identity function is nowhere differentiable. That's not a good notion of differentiation, right? So deleted difference quotient, great for a certain class of examples, bad for the ones we're interested in. So here's the definition. Let me get to it. And this definition will, of course, reduce to the standard one that I just wrote and read over here. You know, this one, the standard definition of complex differentiation in the case that the algebra is equal to the complex numbers. And it will give us a concept of differentiation which is more general for the other algebras we've thought about. So if we'll let U be a subset of A, an open set, and F a mapping from U to A is, my language right here, a function. So if that's a function, then we say it's A-differentiable at P. Is A-differentiable at P. P, which is of course an element of U, provided F is differentiable at P, and just let me emphasize, in the real sense, to be more specific, the Fouché sense. And DFP is an element of the regular representation of A. So in other words, A differentiable for us is going to mean that it's real differentiable. Oh, I'm sorry, that's not my definition. I'm an idiot. Ah! Ah! I'm so sorry. That was going to be a consequence of our definition. If it is A differentiable at P provided there exists, I'm so sorry, guys. There exists DFP from A to A, and our linear map such that DFP is in the regular representation of A, and the following limit holds. The limit as h goes to 0 of f of p plus h minus f of p minus dfp of h divided by the norm of h is equal to 0. And I probably misstated that too. No, I'm okay. So there's my definition. So the reason I wrote what I wrote down just a second ago wasn't wrong in the sense that it's logically equivalent to the definition. I mean, I could just say that that function is real differentiable. What would it mean to say it's real differentiable? What's the problem with the camera? It needs to be higher. Uh-oh. Oh no, I got bumped. There you go. So anyway, so to say it's real differentiable means that there exists a linear function that satisfies the Fouché quotient, right? So essentially that's what I'm saying here. I'm saying that there's a linear function dfp, and it satisfies this Fouché quotient, right? So that actually is real differentiability. So what I was quibbling over is really minor, maybe non-existent. My complaint about what I wrote down before being wrong. All right. So, I mean, immediate consequence is that A differentiable implies real differentiable. All right. So I think it's immediately clear. A differentiable at P implies real differentiable at P. What's real differentiable mean? Again, it just means that there exists this linear function that makes the Fouché quotient vanish. It says that there's a function that is that models the best that matches the change in f near the point in such a way that it's this Fouché quotient. It's the best linear approximation to the change in the function at the point. That's the differential. If such a function exists and this limit exists and is 0, then the function is real differentiable. All right, enough about that. So then the question is, okay, great. So, what about properties of differentiation? And well, before we even get to that, what does this mean about DFP? What does it mean? What is this RA? You guys may have forgotten by now, but this is the set of left multiplication, let's say by B, from A to A, right? Such that B is an A. And how did we define L sub B? L sub B of x is equal to what? It's equal to B times x for all x in A. So the regular representation is the set of left multiplication maps. And what did we learn? What happens if we say take x and y and a, and we look at LB of x times y? Well, by definition, this is b times x times y, yeah? And then we can use associativity. We can repackage that. That's b times x, right? Times y, which is actually left multiplication by b acting on x all times y. In other words, every left multiplication map has the property of right linearity. We can pull scalar multiplication out to the right. Okay? So, thus, in the case that we say the differential at P is in the regular representation of A, that means a couple different things, right? There's two things that means immediately from this discussion. The one is that it's a left multiplication map, right? The other is that it's got this right linearity property. So what's the left multiplication map mean? So, that means on the one hand, by definition, dfp of x, it's equal to b times x for some choice of b, right? And the other hand, we also have this property that we can pull multiplication out like this. Now, if you think back, you might remember what the significance of b is. What is actually b equal to here? Let's let x equal to 1 in the algebra, right? And then what is that? What's dfp of 1 going to be equal to? b times 1. What's b times 1? B, right? So what is b actually? We could write this. dfp of x is in fact dfp of whatever it does to the identity times x, right? Or if you like, I'll write that with a z just so you can see it better. There we go. So saying that the differential in the regular representation, it's very special. It says that the formula for the differential can be written just as multiplication by whatever it does to the identity times the input. This is really, really special. In the big world of possible linear, possible functions from Rn to Rn, this is a very rare thing. Like most differentials do not allow such a formula. So that's one thing we can note. All right. And then, of course, the right linearity. That is something we can use. In fact, it's pretty easy to see that these steps are reversible. So, in fact, a function is right linear if and only if it's in the regular representation, right? In other words, a function is right linear if and only if it's a left multiplication map. So as we're proving things about differentiability, we have two choices. We can either show it's a left multiplication map, or we could show that it has the right linear property for arbitrary inputs. Either would suffice to show that the differential is in fact the regular representation. There is a third viewpoint. What's the third viewpoint? The third viewpoint is that we could say that the standard matrix of the Jacobian of this f, the standard matrix of df, the differential, is in the right representation, the matrix representation of the algebra. What does it mean to say that a matrix is in the matrix representation of the algebra? What's that mean? Remember what the M sub A was? It was just the standard matrix of LB, right? Such that B was in the algebra. So it's the set of standard matrices of left multiplications. So if we say, so if, the standard matrix of our differential is in M sub A, what's that mean? Then there exists B in the algebra such that what? The standard matrix of the differential is equal to the standard matrix of the left multiplication by B. But here's a fun bit of linear algebra trivia for you. You may be learning right now, but you may recall, two transformations on Rn, if they have the same matrix, they're the same transformation. So this immediately implies that DFP is equal to L. So this implies we can drop the standard matrices and just say, well, that means that DFP is equal to L sub B, right? And of course, that implies that DFP is where? It's in the regular representation by A. So that implies that if the matrix of the differential is in the representation, then the differential is in the representation. And put it in words. The matrix of let's see here, put it in words. If the matrix of an operator is in the matrix representation, then that operator is itself in the fundamental representation. And we can go vice versa. Like, what if you went the other way around? If DFP is in MA, good grief, is in the, if it's a left multiplication map, if it's in the regular representation by A, then what? What can we say about, by definition, right? Then the matrix of DFP is where? Well, that's the matrix of the left multiplication by DFP of 1, is it not? I mean, it's that particular left multiplication. That's what the boxed equation says. It says that the differential of an A-differentiable function is left multiplication by the differential at the identity. A-differentiability means the differential is a left multiplication. And so, this is the matrix of a left multiplication map, but by definition, that means that this is an element of the matrix representation of A, right? So I'm trying to get across to you is these are interchangeable viewpoints, right linearity, left multiplication, or the matrix representation of the algebra. These are three different ways we have to look at the same animal, all right? This special kind of transformation Rn, which amounts to a multiplication in the algebra. And to say that a function is A-differentiable means that the differential is such a thing. That's a very strong condition, all right? Any questions before I go on? So, some theorems that we should note for differentiability. Here's some theorems. So let's suppose that F and G are differentiable. Oh goodness, I already lost my, sorry. A-differentiable at P, and let's suppose that C is just a constant, right? Then F plus G and C, F times G and C times F are also A-differentiable. at P. But I should say more. I really should say more. And to say more, I need to give you guys a definition, which is actually based on the boxed equation here. Because there's a word I haven't used yet, which is the derivative function, right? So I should really define for you the derivative function before I go any further. So what's the derivative function? Definition. If, f, suppose that f is differentiable, A-differentiable at each p in U, then we define f prime, which is going to be a mapping from U to A by the rule, and here it is, f prime of p is equal to dfp of 1. So the derivative is the number by which the differential multiplies. So there you go. That's our definition of derivative. So here, I can add some more fine print now, and so what do you think f plus g prime of p is going to be? Very good. We have a winner. F prime of p plus g prime of p. Yeah, it would be very sort of disconcerting if that were not the case, wouldn't it? Now, 2, d of f times g p is equal to dfp times g of p plus f of p times dgp, like that. With the proper interpretation, what I mean by that is that if you feed this a argument h, all right, then the h goes here, and it goes here like that. So this formula I just wrote down is generically true if f and g are A-differentiable at p, okay? So we can write this down. It actually follows from the Uber product rule I shared with you guys the other day. This is true, all right, for all h in the algebra. And then here's the and. If A is commutative, then then f times g prime of p, guess what it's equal to? How about this? F prime of p times g of p plus f of p times g prime of p. So that's, we do need that the algebra is commutative. If the algebra is not commutative, the product rule, well, if A is commutative, then, side note here, oops. Right here, I can't say what I wrote up here without an assumption, which is that A is commutative. So I need commutativity for this. I need A commutes in order to get that A times G is again A-differentiable if F and G are A-differentiable at the point. Now once you have 2, 3 is easy. The differential of C times F at P. Well, let me get to the point here. I don't really care about differentials that much. What I'm after, really, honestly, is that C times F prime of P is equal to C times F prime of P. In other words, you can pull a constant out of an A derivative, if we're willing to call the prime the A derivative. Yeah. There is also a chain rule. All right. For provided the functions are suitably arranged, if we have F composed with G prime of P, guess what? That is equal to F prime of G of P times multiplication in the algebra, G prime of P. So the chain rule generalizes also nicely here, provided that F is actually differentiable. We do need that F is A-differentiable at G of P in order for that to make sense. Just like in the ordinary case, in order to do the chain rule, you need that the outer function is differentiable at the inner function, right? So the proof of all of these assertions, yep.
I just have a question. Why is it G prime? Like, why is it not on the outside of the FG? Outside of the parentheses? Like the prime?
Oh, yeah, that's a typo. Thank you. Good question. It was wrong. Thank you. Yeah. No. That's my larger point here, is that if you know calculus, you know A calculus, a lot of it. Much of what you already know still works for calculus over an algebra. However, you gotta be careful. Things don't commute, and division by zero is perilous because there's more zeros in some sense. I mean, there's zero divisors, right? And those are just as bad as zero in terms of division. The proof of all of these things, it rests on properties of, properties of real calculus. So let me just sketch the proofs for you rather than like writing them out in gory detail. Okay? So first of all, to prove that this, F plus G prime is that, there's a theorem of real calculus that says if a function F and a function G are real differentiable at P, then their sum is real differentiable at P. And that the differential of the sum is the sum of the differentials. All right, so we get that much from just real calculus for part one. There exists d of F plus P, and that function is let me at least give you a proof sketch here. So like for one, by real calculus, there exists, differential of F plus P, F plus G of P is equal to dFP plus dGP, and check it out. So the differential of F plus G acting on x times y, guess what? That's dFP on x times y, right? Plus dGP acting on x times y. But what do we know about x? And we know that the differential of F and the differential of G are both right linear. They're right A linear. So I can pull the multiplication by y out of both of these guys, right? And then you can factor by the properties of the algebra that multiplication factors out like so. And then just repackage it a little bit. That's d of F plus G at the point P, all of that acting on x times y. What have we shown? We've shown that the differential of the F plus G function allows us to pull algebra multiplications out to the right. That proves that F plus G is itself a function which has a differential, right, which is in the regular representation. And that's all we need to do to prove that F plus G is differentiable. Therefore, thus, F plus G is an element of C of P. Now this is my notation, guys. This is the notation for functions differentiable, A-differentiable near P. Fine, to be technical, I mean, there exists some open set on which the functions are differentiable near P. So, to be careful, I really should say F and G are in CP if I'm going to use this language, which means that they're not just A-differentiable at P, they're A-differentiable near P. So, I don't know. You can either prove this at a point or for a bunch of points that are closely attached. All right, anyway, F plus G is A-differentiable. And I think I usually put a little A on there just to be annoying. I mean, why not? Or if I could remember my own notation, it'd be amazing. And then what's the derivative? How do we define the derivative? Well, check it out. So d of F plus G P of 1, right, is equal to dFP of 1 plus dGP of 1. And this, by definition, is F plus G prime of P. And this is F prime of P, and that is G prime of P. So there you go, product sum rule. Let's look at the quotient rule because it's, I mean, not the quotient rule. let's look at the chain rule because it's not too bad. And it might actually be instructive. So the chain rule, so we're supposing that F is an element of, it's got to be A-differentiable near G of P, and we need that G is A-differentiable near P, okay? For this to make sense, then by real calculus, what's real calculus say? Real calculus says that the differential of F composed with G, goodness night, well, that's not even saying, F composed with G at P, here's the chain rule that says that the d F G of P composed with d G P. DGP, wait a minute, no, GDP. Anyway, so there you go, that's just the ordinary chain rule, which we prove in advanced calculus. So consider, if we take the differential of the composite at P and we feed it x times y, what happens? Well, that's dFG of P of dGP of x times y. All right? But we have right linearity of the differential of G, so we can pull out the multiplication by y on the inside, right? So we get like that. But then, well, we also know that the differential of F has got the right linearity, right? Shush. Ah, quiet. Silence. I don't care about Elon Musk. Stupid. Oh, it's actually my brother. All right. Not to be confused with Elon Musk. Anyway, so the point is we can also pull this out by the A-differentiability of G of F at G of P, rather. And so we get dF G of P of dGP of x times y. Thus, dF composed with G at P is an element of the regular representation of A because it's right A linear. And what's the derivative? Well, we can calculate, right? So what's the differential of the composite at P acting on 1? It's F. So if I could follow my own calculation for a second here, that's supposedly d F G of P of d G P of 1 But what's dGp of 1? Well, dGp of 1 is, this is g prime of p, right? And so what we have is f, well, we have df g of p acting on 1 times g prime of p, again by the right linearity. But what is d f g of p at 1? That is exactly f prime of g of p by our definition. So there you go. You got the chain rule. You got sum rule. You got a product rule. But admittedly, the product rule is technical. I'll show you in a second. Now, so in an ordinary complex analysis class, everything I'm just doing would just be like gory manipulation of limits and difference quotients. Right? We'd still be obligated to prove these things if we cared about details. It's just there the proofs would be couched in like difference quotients, right? Here, what I'm doing is I'm using advanced calculus to get the core of the theorem, and then I'm just showing that right linearity filters through the differentials the way you want to give us these differentiation rules. Listen, at the end of it, we have that the sum and product and composite usual rules of calculus still hold for A calculus. And that's really nice because that means things we derive from the sum, product, chain rules are still going to be true for A calculus, right? So the thing we're going to be talking about for the most part the rest of the week is the Cauchy Riemann equations, right? So I'm showing you some sort of like general features of the A calculus, but for a specific function you might want to know, is it actually A differentiable or not, right? And so just to give you a snapshot ahead, next class again we'll be looking at the Cauchy Riemann equations, and you can derive those pretty easily from this already. So like let me just say a word here. Cauchy Riemann equations, or I would call them A Cauchy Riemann equations. They're essentially just contained in the right linearity. If you look at dFP of, say, EI times EJ, well, that's equal to dFP of EI times EJ, right? Let's see here. And let's just suppose commutative for the sake of not going nuts for a moment. Let's assume commutative. Then this would also be equal to dFP of EJ times EI, right? Which would be dFP of EJ times EI using that right linearity. And these should be equal if the algebra is commutative. But the thing is that this is exactly partial f, partial xi at the point P. So we have partial f, partial xi at the point P times EJ is equal to partial f, partial xj at the point P times EI. If these equations are true for all I and j, these are called this is one formulation of the Cauchy Riemann equations. And so if you can check that these equations hold true for a given function, it implies that the function is A-differentiable, provided that you also have continuous differentiability of the function. That's what we're talking about next time, right? So it's going to get a little bit more specific and a little less out there next time. I just wanted to give you a flash forward. Anyway, more on that next time. For the remaining couple minutes of class, let me show you the beast, which is part 3 here. Yeah. And then we'll finally get to the question Sam is about to ask me about the generalized conjugate. Yes?
I was going to say,
Oh, it wasn't about that. Anyway, go on. Yes.
did we show that,
I assume his questions are about generalized conjugation, as they usually are.
did we show that this definition, like when you, in the
that is contained back in, I mean, I think you'd have to, come on. You can do it. You can do it. You can do it. Come on. Yes. Ah. So, Sam, the back here, I'll get to it eventually. Connections with our past and future. In here, I show that if you have a function from reals to reals and it's Fouché differentiable, then it implies that the differential is the regular derivative times the argument. That's the formula for the differential, and vice versa. So real differentiability implies Fouché differentiability for real function. And then by essentially the same arguments, you have that, the differential of a function from r to Rn, it's going to be the velocity of the path times h. So like the velocity of the path gives you the Jacobian matrix, if you will, for a function from r to Rn. And I don't know, I guess, okay, fine. Oh, hey, I think Sam has pointed out a homework problem. Thank you. That might actually be missing, given my current presentation. Thanks, Sam. All right, so yeah, I'm not sure it's absolutely clear that the regular definition, which I stated at the start and have erased at this point, and the definition of A differentiable coincide in the case that A equals to C. That is something we'd like to check on. I don't think it's that hard. I think it's essentially that connections with our past and future calculation, except with a complex instead of a, it should be similar. This is an example which always fails to be A differentiable, and also involves the general conjugation that Sam has been dying for me to talk about. I'm talking about it for the first time right now. If you have algebra variable x1 through xn en, then the second conjugate, we just put a minus on the second one. It turns out that that's going to give you a function which is not A differentiable, but more on that later. I talked about this today, that there's an equivalence between right linearity, left multiplication maps, and the matrix being in the regular representation. We have these three viewpoints. I define the derivative to be equal to the differential at 1. Here is the proof of the sum and the product rule that I just went through, right? So here's the proof of two. I have a proof of 2 also that stands alone without using the Uber product rule. So if I have two functions, f and g, excuse me. This is just proof of c times f being differentiable, not to the product of f and g. But this actually gives you a sense of how you'd prove it without relying on the product rule. You can actually face the Fouché quotients directly. You can show that the Fouché quotient of f, of like the algebra times f, is actually the same constant times the Fouché quotient of f. But the differentiability of A differentiability of f implies this goes to 0. And then we had a product rule for limits before. So if this goes to 0, then so does c times that. And that going to 0 amounts to this going to 0, which is to say that that whatever L of h is works for the Fouché quotient, but L of h is exactly c times df p of h, which is to say that we can pull scalars out of the derivative. What I really wanted to show you, though, since I've got this monstrosity out in front of us, is the product rule. And so this formula already, because I really don't want to talk about this another day, this formula was already given to us in the Uber product rule I shared with you guys the other day. And if it's commutative, it reduces to this. So here's the deal. So if f times f times g is real differentiable because it's formed by a sum and products of, if f and g are continuously differentiable, then so is f times g. That's easy enough to prove. And then we have this formula for the differential from the Huber product rule, and then you can prove that you can pull out the scalar to the right like that, which then says that f times g is right alinear, which says that the product of f and g is alinear. But it was important for the algebra to be commutative because I had to pull this w past the g of p here. And if I can't do that, we're out of luck. So we need commutativity in order to move the w past the g in the product rule in order to get the product rule. And I have an example of what happens when, I mean, it's possible in a non-commutative algebra to still have differentiability of the product, but I actually have an example here where it shows you that we have the product of f and g is a-differentiable, but the other way around, g times f is not a-differentiable. So you get some really weird stuff if you deal with non-commutative algebras in terms of the differentiability properties in terms of our definition. So that's what this example here is. It's just a horrible, horrible six-dimensional algebra where I have an explicit function where f times g is g, and that's a-differentiable, but g times f is actually something which is not a-differentiable. I don't really expect you guys to understand the nuts and bolts of this example. It's just kind of for your general information purposes, right? If you can work the homework in here, you should be fine. The notes have some things which are harder. I'm still trying to cull out, I'm trying to remove the stuff I don't want you to read, but it's a process, yeah? Anyway, thanks guys. Just